We live in a world that is becoming interconnected. Imagine a tool that connects all your data points so you can visualize in real time, seeing the impact of proposed changes, avoiding costly mistakes, extending your model to design and operational uses. Our vision is to become the leading process digital twin solution for improving the design and operation of complex systems.
We picked this verbiage intentionally, transitioning to the digital factory, where we know it's not going to be something that we can do in 6 months. It's going to be a transformation not only in our operations, tactical, and technical work, but as much as that, it's going to be also a cultural shift in how we increase our pace of innovation as we transition into Industry 4.0. It's going to take a shift in, like I say, culture and the way that we do business as much as it is a technical challenge. So while we're not quite there yet, we're still very immature in our model, our maturity model. We are moving very diligently in the right path. So like Sam said, I'm a tech fellow at Lockheed and IT. I've been with Lockheed about 12 years now. And Tony is, I view Tony as an internal customer of our data. I am responsible for the data pipeline, building a secure, low latency pipeline into the cloud, the data lake, based on standards. We don't want it to become a swamp. And then I view Tony as an internal customer who then adds the layer of business value and unlocks those use cases for that data. But I think we covered our backgrounds pretty extensively. So what is the objective of the talk? Really the objective is we're going to illustrate slide by slide how, the how we do IIoT, the Industrial Internet of Things, and how we get these machines to tell us how they feel and when they don't feel well, and how we can predict things. And then we'll tell you the why, and that's the business value piece. That's Tony's piece. I'll turn it over to him in a little bit. So the way that we're going to do that is the way this works for external, I typically give a company overview, because I know not everybody on the call is familiar with our business, especially aeronautics specifically. So I'll talk. I've got a slide or two on that, and then I'll go into the details of how we actually connect these machines and transition from an IT world down onto the shop floor into an OT world, operational tech world, the infrastructure and hardware, and some of the security and some of the data model piece of that, and why we use a common ontological framework, and why data standards are critical when you're talking about IIoT, because these machines do speak very disparate languages, and the physics of the systems in some cases are very different. So an autoclave behaves very differently than a Fanic paint robot, of course. So, and then Tony will go into some advanced neural network LSTM models to derive at least some of the early use cases. Like I said, I think we're pretty early on in terms of our total use cases, but Tony's already been able to extract some pretty tremendous value, ROI, from this, and we'll go into that. So Lockheed Martin is kind of segmented into 4 main business units. We've got the rotary and mission services, or rotary and mission systems. That's mainly the Sikorsky line of business and the littoral combat ships. They build the Black Hawk, the CH-53K heavy lift. There's MSC, which is missiles and fire control. They've got the THAAD program, the Terminal High Altitude Area Defense, PAC-3, and some of the autonomous ground systems for the Army, a whole bunch of products there. And then, of course, Space Systems. They used to build the external fuel tank for the space shuttle. They've got the Orion program. They're heavily involved with Mars missions and NASA. And then, of course, Tony and I work for aeronautics, and our main lines of business typically carrier aircraft and fighter aircraft, although we do have Skunkworks, ADP out in Palmdale, where we've got Black Ops programs, you know, hypersonics and all that. So aeronautics typically, I took it from the annual report last year, we're about 40% of the company in terms of net sales. And yeah, we've got some commercial business as well, but typically primarily a defense, you know, Department of Defense contractor. Our big program there below is the F-35. I think we've got about 14 or 15 international partners, and of course, all three of the major services, the Marine Corps buying mainly the STOVL variant, the vertical takeoff and landing variant. Navy's looking to replace some of their aging F-18 fleet with a carrier version. And then, of course, the Air Force, the United States Air Force as the largest customer with the long-range version. So that's a little bit about the business. Feel free to stop me at any time, like Tim said. I don't like talking to slides. I like talking to people. I would much prefer this to be in person, but it is what it is. So with Industry 4.0, this buzz term that's been with us for 4 or 5 years, everybody's talking about Industry 4.0. What does that mean? How do we get there? Industry 1.0 was the industrial revolution that we're all used to with history class. And I know with this audience, this is a technical audience, so I don't really have to go through this slide as much detail as I would for a non-technical audience. But the industrial revolution happened. We figured out how to do processes using machinery, right? And then along came electricity, and we figured out how to do mass production. Much better than a human manual process, right? And then along came the internet, and then all of a sudden we were connected, and computers went from the size of a room to we've got an iPhone. You know, I'm talking on an iPhone right now. So what's the next stage that we're in right now? That's the cyber physical revolution. In order to get to the digital factory, we're going to require our machines to talk to each other and do more autonomous activities. We're going to shift the burden from our operators to the machines themselves to tell us when they're about to have an anomaly or they're about to shut down unexpectedly, so that we can predict that and shut the system down. Or we can do maintenance on a condition, physics of the condition of the system schedule rather than on a time-based schedule. So change the filter after X number of hours versus change the filter right now because we can actually see the system is being bogged down, or a Z motor axis load is way out of tolerance. Go shut it down and replace the Z motor axis before we break something bigger, right? So that's where we want to do near real-time use cases. We're seeing latency less than a second going from the shop floor to the top floor. That is the GovCloud data lake. So we think we can get there. Like I said, it's not going to be a 6-month project. We know it's going to take a few years to get there, and we're moving quickly. So in order to get to the factory of the future, in order to fully realize the benefits of Industry 4.0, we believe that has many facets. You know, autonomous vehicles is one of them. But the industrial Internet of Things, the project that keeps Tony and I busy during our work schedules is a key enabler of that. We don't think we can get to the digital, factory of the future without IIoT. So how do we do it? The reference architecture on the edge starts with machine types. So we do a comprehensive analysis of each machine class, asset class. So we classify all of our thermals together. For instance, like autoclaves. It's essentially a curing oven that has, let's say you put a wing skin in it and the part comes out cured, right? Intense heat and pressure. So the data types, those thermocouples, the door locks, the pressure, that data type is fundamentally different than a paint robot or a wing drill that's operating at a much higher speed and has much smaller tolerances, right? So these machines give us data and a myriad of data types, or let's use the analogy of human language. We found out very quickly in IoT, we needed a Google Translate for machines. We needed something so that these machines can be mapped into a common framework, a common ontology, if you will, for analyzing the data. And you don't have to go back very far. If some of the folks on the phone might remember the Mars Climate Orbiter from the late 90s. If you're analyzing data and you don't get the units common in a standard format, then that can have huge negative implications on the back end, what Tony's going to do. We don't need mistakes like that. That was like $100 million mistake. We slammed an orbiter right into the surface of Mars because of something as simple as a data conversion, a SI unit conversion. So all of our data is mapped into a common ontological framework with common units, common semantic model, and I'll go into that in a little bit, but get invited to a meeting here. So you can see how that's important. So how do we get a Google Translate to machine? We're using an open protocol, a non-proprietary protocol called MT Connect. It is currently an ANSI standard, American standard, and within 3 to 4 years we expect it to go ISO standard. And it really is a Google Translate for machines. So what we're doing is we're installing a piece of software that maps the native unit from the OEM, the native language, if you will, the data language that the machine speaks natively from the OEM into a common framework called MC Connect. And we install that piece of software on the asset controller, which is the PLC, an Allen Bradley or Fennec or Siemens. There's probably at least a dozen different types on the shop floor. And that's where the machine operator will stand if they need to do a feed rate override or an emergency stop, an e-stop, or monitor the recipe file, because the vast majority of our machines are CNC machines, and MC Connect made the most sense for 90-95% of our use cases. So we take the data and we map it into a common framework, common ontology, and then the data gets sent to a Cisco switch sitting inside a smart box. So you can think of a smart box out on the factory floor as a ruggedized container for our data. It's dust-proof, fireproof. It really is built for an industrial environment. And if you've ever been to a factory floor, you know that it's loud, it's noisy, it's dirty, and we don't want our data in an environment like that without the appropriate protection. So we're procuring smart boxes and deploying them almost on a one-for-one architecture, one machine to one smart box. There's a number of reasons for that. One is security. The other one is data latency. And we don't want to lose data. So we found out that our IE4K switches, our Cisco switches that we currently are using, we couldn't containerize those. We couldn't host our MT Connect agents in the cloud. So we're going through an update process of updating to the 3400 series so that we can have a more robust CPU, more RAM, more storage, because our data is going into this as a buffer. We have a finite, limited amount of time to harvest the data from the switch via an agent harvester. So we'd really like to host these agent software in a container. That way we can actually host it anywhere in a virtual machine somewhere. So the reference architecture, I think we've got right now, Tony, you can correct me if I'm wrong, I think we've got 11 different asset classes connected right now. And we have aspirations to scale up to over 150 different machines by the end of the year across 3 different sites: Palmdale, California, of course, Fort Worth, where we built the F-35, and then Marietta, Georgia, where they've got the C-130. So that's the shop floor architecture. And if we move into the data piece, this is the MT Connect device semantic model. This is what I was talking about earlier that I couldn't illustrate with words, but a picture's worth 1,000 words. So for each asset class, we go through a pretty rigorous data definition process. So we turn the machine on, we feed some initial data to us, and then we work with the OEM or we work with a supplier like TechSolve or 5ME to build an adapter that tells us exactly which components map to which systems and which devices, sub-devices. So for instance, a hydraulic power unit might have an electrical system, and it has its constituent subsystems. And then it also has a cooling system, and it also has actually the hydraulics itself and a platform, so a physical system as well. So we need to know this. The data scientists need to know this. The operators need to know this. The semantics are the great value of having a data standard, so that you can do post-mortem analysis on failures, so you can do real-time analytics monitoring and see where the anomalies are coming from, and a whole bunch of different use cases. So being able to do a state machine or a digital twin, these future use cases, this kind of data architecture is going to enable that. I think there's a lot of value in the future from having, it takes a lot of extra time than just turning the machine on and sending random data to the data lake, right? It takes a lot more cost and effort up front, but we think it's worth that price to unlock the number of use cases in the future like digital twinning. So a little bit more about standards. I wanted to kind of break the ice a little bit. I know that data is a little bit of a boring topic, so we all know that with standards, there's too many standards, right? And if we try to corral them all into one standard, well then, 6 months later we're going to have just a new standard, right? The side by side with all the rest. That's typically what we don't want to get into. When we created this data model and data standard, we didn't really want just another competing standard with everything else. We wanted something that truly made all the business units at Lockheed Martin, as long as they were compliant with this data standard, then it was very critical for us to have a data lake that's based on standards, so that Tony can do his job, so that the machine operators can do CBM, condition-based monitoring. So we wanted to base it on a standard that was built for this use case, MT Connect, of course. We're harvesting the data and transforming it into JavaScript object notation. It's a lightweight protocol. Our observations are sent to the data lake in JSON format. We're using AWS GovCloud for our data lake, and an edge software deployed on our virtual machines called Greengrass. And what Greengrass allows us to do is transport the data via MQTT and do some of our security layering at the edge. We have built a custom Java client which interrogates the MT Connect agent and transforms the data into that common data model. Like I said, with MT Connect, all the units come standard. So if you're sending temperature to the data lake, it better be in Celsius, not Fahrenheit or anything else, Kelvin. If you're sending rotary axis speed, it's revolutions per minute, so we don't have any conversion issues. If you're sending data in timestamp, you better be sending the timestamp in UTC, Zulu time, and it's ISO 8601 standard format, not Unix epoch time or something like that. So our JSON has a very specific schema. We have a JSON schema, and we have a Lambda function at the edge running on Greengrass to certify that the data is in that schema and the units are in MT Connect compliant format, and et cetera. Your date time is UTC and all that before we allow the data into the data lake, so that we can keep it a data lake and not a data swamp. We have built the data model to be robust enough to handle non-MT Connect compliant devices. We know that Haystack is coming for HVAC systems. We know that QIF, for quality information is coming. We know new standards are going to be there. So we tried to build our data model robust enough to handle those types. I did have a sample JSON that you could look at. I was not able to get that approved through our PIRA process in time. Very rigorous process on what we can illustrate as an external talk. So that's why I couldn't make this last minute change. The sample JSON is listed as notional. I intended to show that, but I had to mix it at the last moment. Apologies for that. So what does the data lake, data pipeline look like all the way to the lake? On the last point, I did have a much more detailed framework architecture diagram to show that also got rejected. It shows a lot more of our managed services in the GovCloud, like Elasticsearch and our use cases and the data flows and all that. But this will have to do for now as a generic picture. Our data starts at the shop floor, like I said, with our autoclaves and milling machines and wing drills. We write a software adapter to map it into MT Connect and the semantic layer so that we can collect that data. We send it to a smart box acting as our agent. And then we built a custom Java client sitting on a virtual machine at each site, and that will be actually Dockerized soon. It won't have to sit in one location. It can be anywhere once we get our agents upgraded. We have a broker, a publish subscribe broker, sending the message query telemetry transport, MQTT ISO standard up to the data lake through Greengrass, which is also an AWS managed service at the edge. It's sitting on that same virtual machine actually that the Java client is sitting on. And then the data gets sent JSON by JSON, payload by payload into IoT Core, AWS IoT Core. And then from IoT Core, which is subscribing to the specific topic that Greengrass is sending. It's, the standard pub/sub architecture. Greengrass is publishing to a topic, and then the IoT Core is subscribing to the same topic. So we're getting our payloads very quickly. Like I say, the latency we're seeing right now is less than a second from the shop floor into IoT Core. And then from IoT Core, we can route it anywhere we want using Kinesis. Kinesis is just another broker. Kinesis Streams or Kinesis Firehose, depending on the use case. And we can send the metadata to a different NoSQL database like Dynamo if we wanted to. Tony can spin up an EC2 instance and run Domino for his machine learning model. But the great thing about using AWS GovCloud is they've separated compute from storage. So we really can't run out of storage. We're sending all of the master data to S3. And then once the data scientists give us the okay, it's okay to archive that, then we shift it over to Glacier, and it's dirt cheap. It's a lot different than when we first started in 2017, where we had an on-premise Hadoop cluster, where we really had to worry about, are we going to fill this thing up, and we had to do capital expenditure forecasting and all that. Well, with the scalability of S3, we can send whatever we want. It's cheap, and then Tony can go use the compute. Spin up an EC2 cluster in an hour, use it for an hour, and then spin it back down, and, it's paid by the minute So we think that's a game-changing thing. We love the cloud. I love AWS. It has a whole host of microservices that we're not even using yet because they're not approved for the GovCloud yet, where we're kind of restricted to microservices that are managed services rather that are GovCloud approved. So lots of exciting things going on. That's the data piece. That's my piece. It's kind of a whirlwind introduction. I try to go as quick as I can because I know we're time constrained, but I'm happy to take questions now or later before I turn it over to Tony. He's got the next piece.
So what we've been primarily focused on in enterprise integration is leveraging this historical data in the data lake that Brian just explained, the right side of his last chart there. Leveraging that data to create some machine learning models so we can add value to some of the self-service analytics. So I'm going to briefly introduce the first advanced analytics use case that we applied to the data. So first thing I'll talk about is the overall approach that we've taken to modeling. So when we first started this, we had been pursuing this sort of more traditional physics-based approach, but we started to identify some real drawbacks to that. So namely, that type of modeling requires significant work by a knowledgeable human. That person needs to be knowledgeable of both the physics of the machine and also the modeling approach. Another issue is that the work that you spend creating a model for one machine class isn't transferable to another. So in other words, it doesn't scale when we add new machines. So we changed direction and pivoted to a more cognitive approach where we use a machine learning model as a baseline. So the advantages here are essentially the opposite of the drawbacks of that physics-based modeling approach. The meta models are agnostic to the machine class. We get to meaningful results quicker since it takes less human effort, and then it's scalable to new machine classes. Now there is a drawback, and so the drawback is that if we use just a machine learning model alone, we may not be extracting all of the value that we could, using our physics or subject matter expertise of the individual machines. So the idea is to put in place a framework where we can augment that baseline machine learning model with some more traditional modeling through either what's called pre-estimate or post-estimate fusion. So pre-estimate fusion it's just things like manual feature engineering based off of our knowledge or traditional modeling approaches. And then post-estimate fusion is like an ensemble of models, so an ensemble of a machine learning model and a traditional physics-based model. So the specific model that I'm going to talk about is an LSTM, stands for long short-term memory recurrent neural network for anomaly detection, and it's not an original idea, so here's a reference. It's a very well-written paper, and you can read it for free online or download it at this URL. All right, so for those who are unfamiliar with LSTM networks, it's a type of recurrent neural network. And a recurrent neural network is just a neural network that can remember past observations essentially through a feedback mechanism that allows it to learn relationships between the current observation and past observations at different time lags. So that makes it suitable for applications where the input to the model is a sequence. So in our case, the input is a time sequence of observed machine states. But simpler recurrent neural networks run into a computational issue where small errors due to finite precision arithmetic add up over time. And that sort of limited their effectiveness in practice, but a slightly more complex network, the LSTM, overcomes those issues, and it's been very successful in the past few years in some high-profile applications like Siri and Alexa. So the basic idea is that in addition to learning those relationships between the current and past observations, there's also a mechanism whereby the network also learns what's important to remember and what's okay to forget. So up here, this is for reference what a simple recurrent, vanilla recurrent neural network cell might look like. You've got the current observation coming in, and then you've got the output from the previous observation, and then your output out the other side. So the LSTM adds an extra bit of complication through 4 additional parts. You've got the cell state, and you can think of that as the persisted memory of the cell. You've got a forget gate that controls the extent to which memory is persisted. You've got an input gate, and that controls the extent to which a new observation is added to memory. And then you've got an output gate, and that controls the extent to which memory is used in the new output. All right, so a common approach to anomaly detection is to compare a predicted state to an observed state, and then presumably if the observed state differs from the predicted state, then there might be something abnormal going on. So the prediction typically comes from either some physics-based model like in a Kalman filter, or a statistical model like the ARIMA models that econometricians use to detect anomalies in financial data. But like I talked about on my first slide, so we're using a purely data-driven approach. So the model that we're using for the prediction part of this, at least with the baseline, is learned entirely from the historical data without any assumptions. All right, so with the single variable, it's pretty straightforward to just look at the difference between the predicted and observed values, but with more than one variable, it's a lot more informative to take into account the correlations between the errors for different variables. So as an example here, suppose our original error distribution looks like this plot here on the far left. So clearly an observation that falls, somewhere down here or up here is anomalous, but how do you quantify that? How do you put that in code, right, to be able to detect those as anomalies? So what we do, and these are the basically you can think of them as the residuals, right? So that's the difference between the predicted and actual. So what we do is some matrix algebra to transform this error distribution to be spherically symmetrical about the origin with a variance of 1 in each direction, and that makes the errors much easier to interpret. And now we can apply some rule-based flags for anomaly detection. So what this matrix algebra is doing is, so first we just subtract off the mean, right, that centers it around the origin. We multiply it by this matrix of eigenvectors to align it, to align the eigenvectors with the axes. And we scale it by the eigenvalues, right, so that the variance is 1 in every direction. And then we put it back to its original orientation by multiplying it by the inverse of that eigenvector matrix. So then the end result of this is you get this nice spherically symmetrical distribution around the origin. And then we can apply some easy rules-based things like, anything that lies outside of an appropriately sized hypersphere or hypercube, we can flag as an anomaly. Or we can just do, take the L1 norm or the L2 norm distance from the origin and call that the anomaly metric, right? And then you might have some thresholds around there. So here's some of the tools that we used. So I used the Domino Data Lab environment. That's like a cloud-based tool for doing collaboration for data scientists. And, we've got a lot of high-powered computer GPU computing instances that we have access to through that. RStudio is the development environment. For the fitting of the neural network, there's a Keras package for R. Uses a TensorFlow backend. All the NVIDIA technology is built in that comes with the Domino Data Lab instances. We've done some experimentation with looking at the results real time, applying the predictions real time, and viewing the results in a dashboard through Grafana, and streaming the data through InfluxDB. These are open source tools. And then our facilities engineering customer is visualizing the data using Splunk, which is not open source. All right, so the last thing I'm going to show here is an example of how this might look in practice. So this is some sample analysis on a machine on our F-35 production floor. It's called a FOG, flexible overhead gantry milling machine. And this particular machine failed in January of last year. And that's kind of a big deal because there's only 2 of these machines, and if they were both to fail at once, then that would hold up the production line. So the first thing we looked at was that total anomaly metric. It's basically the L1 norm that I was talking about, distance from the origin of those residuals, normalized residuals. And so that's what's plotted here. And if you squint, you can sort of see that it's rising up. At least the mean here is sort of rising up, right, leading up to the failure. But the next step, and I didn't mention this, but another advantage to the way that we've sort of done this is that you can drop, you can take any sort of subset of the variables to look at. So, right, so I can do an anomaly metric that's based off of, one section of the machine, right? I might look at all of the variables that have to do with the movement in the z-axis, and I can get an anomaly metric for that. I can look at an anomaly metrics for each variable individually, and that's what we did here in this case, was to look at the anomaly metrics for each individual variable and see if we could find ones that were trending upwards or trending upwards the most leading up to the failure. So this was the variable that we found that had the highest, steepest upward trend leading up to failure, and this is the temperature of a motor that controls motion in the z-axis. and this did, in fact, turn out to be related to the failure. So what we're fairly certain had happened was sometime prior to the failure, the machine hit a hard stop in the Z-axis direction, caused some damage to some components, and then over time, and the motor that controls the motion in the Z-axis became damaged. So you can see, so the metric has been normalized here. So we're expecting to see values between 0 and 1, and that's what we're seeing here. Towards the end of the year, first part of the year, and then you start to see, in mid-January, you're hovering up around 1, which is already abnormal, and then right leading up into the few days right prior to failure, we're consistently up above 1, right? So, hindsight is 20/20, but the implication here is that we possibly could have seen this failure coming, days in advance if we had been looking at the data in this way. All right, so that's it for my part of it. This was, some takeaways that we'd like you to take away from the presentation here today. So we hope we've demonstrated that IIoT is a key component or driver of the future factory. The data pipeline enables secure, scalable, rapid value delivery. And then, the webinar series here is the value of information. So I hope we've demonstrated how you can extract value from this type of data or information. And here's our contact info, and I think we can open it up to questions for either myself or Brian at this point.